is problem 37 from the Schrödinger equation. In this problem, 8 neutrons are trapped in an atomic nucleus, which we are going to model as an infinite potential well. And the length is 5 femtometers, so L is equal to 5 femtometers. Remember, a femtometer is times 10 to the negative 15th meters. In part A, we want to find the total kinetic energy of the 8 neutrons. Now, keep in mind here, when we did the infinite potential well, the potential energy inside of the well is 0. So this is for the total energy. The total energy is U plus the kinetic energy, but here U is equal to 0, so the total energy is equal to the kinetic energy for a trapped neutron. So part A, we're finding total KE for all 8 neutrons. We have mc squared for the neutrons here, and I'm modeling it as an infinite potential well, so this is the energy of 1 neutron. So we're going to find the energy of all 8 neutrons and then add them all together. However, take a look at, this is page 9 in your textbook. And here they give us the Pauli exclusion principle, which states that no 2 identical fermions, and a neutron is a fermion, can occupy the exact same quantum state. So only 2 neutrons and 2 protons can occupy the lowest energy state with 1 spin up and 1 spin down. In this way, the well is filled from the bottom up as indicated. In your lowest state, you can have 2 neutrons. Since neutrons are different than protons, if you have neutrons and protons, you can have 2 of each in the lowest state, and then you fill it up from there. So we only have neutrons here, so we can put 2 in each state based on the Pauli exclusion principle, which you can read more about on your own. And so to fill up all my states with 2 neutrons in each state, and I have 8 neutrons total. In the first state, when n is equal to 1, I get 2 neutrons. In the second state, I get 2 neutrons. In the third state, I get 2 neutrons. And in the fourth state, I get 2 neutrons. And that gives me 8 neutrons. Because to calculate the total energy, I want n squared. When n is equal to 1, n squared is equal to 1. When n is equal to 2, n squared is equal to 4. When n is equal to 3, n squared is equal to 9. When n is equal to 4, n squared is equal to 16. Okay, and then I'm going to add up the energy for all of the particles. So first, let me calculate what I get for hc squared over 8mc squared L squared. So for 1 neutron, I have n squared is equal to hc squared over 8mc squared L squared. Because I have L in femtometers for hc squared, I'm going to use 1240 mega electron volt femtometers, and that's squared, divided by 8 times mc squared, which is 939.6 mega electron volts, and L is equal to 5 femtometers. So L squared would be 25 femtometers squared. Femtometers squared cancels out. Mega electron volts over mega electron volts squared divided by mega electron volts gives me the answer in mega electron volts. And this is 8.182 mega electron volts. So I want to add up the energy for all 8. So I'm going to add up for each proton what I have here, but since everything is being multiplied by 8.182 mega electron volts, I can leave that at the end. So I have 2 times n squared when n is equal to 1. So for my first 2 neutrons, it's 2 times 1. For the next two, because I have 2 of them, it's 2 times n squared, which is 4, plus 2 neutrons when n squared is equal to 9, plus 2 neutrons when n squared is equal to 16. What I have here, 2 times 1 plus 2 times 4 plus 2 times 9 plus 2 times 16 is 60. So this is 60 times 8.182 mega electron volts. This is the total kinetic energy for all 8 neutrons, and that gives me 491 mega electron volts. So that's my answer for part A. For part B, if 4 of the neutrons changed into protons, calculate the new total kinetic energy and ignore the mass difference between protons and neutrons. So we're still going to use this for mc squared, which means I can still use what I had here for part B, ignoring the mass difference. E for the proton or the neutron is equal to n squared times 8.182 mega electron volts. So I need to make a new table like this for when I have protons and neutrons, and if 4 of the neutrons changed into protons, now I have 4 neutrons and 4 protons, and I can put 2 of each in the lowest state. So when n is equal to 1, I have 2 protons and 2 neutrons, and n squared is equal to 1. When n is equal to 2, n squared is equal to 4. I have 2 neutrons and 2 protons in that state. And that's 4 neutrons and 4 protons, so that is everything. And then Ke total is, I have 2 neutrons when n squared is equal to 1. I have 2 protons when n squared is equal to 1. I have 2 neutrons when n squared is equal to 4. And I have 2 protons when n squared is equal to 4, and this is all being multiplied by the 8.182 MeV, and that gives me, when I add everything up, what's in brackets here is 20, so it's 20 times 8.182, which is 164 mega electron volts, which energy is smaller than what we have here because you can put more of the particles in the lower energy states when you have a combination of neutrons and protons. And that concludes problem 37.